Welcome back to part 2, Abstract Theory. Our plan is to develop in this part basically all the necessary mathematical tools to discuss non-equilibrium statistical mechanics in parts 3 and 4. So that means some parts, like this part about Markov jump processes, will be a bit heavy. But by going through this heavy part, our parts 3 and 4 becomes easier. So anyway, let's get started. So I start with probability. I think most of you know about this, so please go quickly. Basic concepts in probability theory. So we consider a physical system like we discussed in part 1, page 36 of part 1. So let's go back to part 1. We are interested in, like, for example, in classical spin system, especially classical discrete spin systems, like the Ising model or the Potts model. So in this case, this is Ising model. You have a lattice, and on each lattice site, you have Ising spins and Ising spin, and each Ising spin can be either up or down. So there are like 15 spins in this case. So there are 2 to the 15 different spin configurations or ionic conductors. In this case, you have, again, lattice, but each lattice point represents potential minima for these ions. And each ion is sitting in one of these minima, local minima, and from time to time it moves. So this is one configuration of a particle configuration. Okay, let's go back. So that this is we are interested in that kind of system. So we are interested in a classical physical system that have discrete microscopic states. And here microscopic states means like particle configuration. So, you know, if you by a microscopic state, I mean a particle configuration, not the position of a single particle, but a particle configuration means that if you have like 100 particles, then I tell you where they are. That defines a particle configuration. That corresponds to a microscopic state. In spin system, then spin configurations are microscopic states. Okay, this is, of course, this is a very physical way of saying thing. In mathematics, people call this elementary events, and I call these microscopic states like J 1 to, and it takes value from 1 to ... omega. Omega can be a huge number, okay? But anyway, we can number these microscopic states. Okay, events. I denote by by AB events, and an event A is an object which is either true or false when for each microscopic state J. So if you are given a microscopic state J, and then event A is either true or false. Okay, and probably I think you know this. And I denote by F hat G hat the state quantities. In mathematics, they call this random variables. And a state quantity F is an object which takes a definite value Fj when you are given a microscopic state J. Okay, so actually state quantity is a terminology used in thermodynamics in a slightly different way. So this may not be a standard terminology, but this is a consistent terminology in this lecture, because we are going to have jump quantities and path quantities, so on. But anyway, okay, so this is a basic state quantities. Okay, and probability distribution is a collection of omega numbers, p, pi, p1, p2, ... p omega, and I denote it like this, both p, and sometimes represent it as a vector like this, or you can simply write it like this. And this entries, pj, is called the probability of state j. And the condition that this should be called a probability is that each pj must be non-negative, and if you sum over the all pj, it gives 1. So these are the conditions for probability, and actually these are the only conditions for probability. If pj satisfies these 2 and 3, and then we can call it probability. And the collection of probabilities is called a probability distribution. Okay. And now again, this is very, very standard. So suppose that A is an event. and we are given a probability distribution P. And then this probability P of A is the probability of event A, and this is defined like this. And here chi j A is a characteristic function, and it takes value 1 if A is true in this state J, and 0 if A is false in this microscopic state J. Okay. Also, this is either 0 or 1. So actually, in this, so if you don't have this, this is of course 1. And here in this summation, we are restricting sum to J in which A is true. And this is expectation value of a state quantity F. Well, this is just simple. If you are given probability distribution, then you just consider product of Pj, Fj, and sum over J. Good. And this is a fluctuation of F, or the standard deviation of F. This is, again, the standard notation. And probably this is easier. This is F, the state quantity, and this is a difference of F and its expectation value. And you take square and expectation value, and then you take square root, because this has a dimension of F squared, so you want to have something with dimension of F, and you take square. Or you can, can be written like this, and this tells you, this just tells you how much F fluctuates around its expectation value. This is not related, but I had to define it somewhere. This is a very special example of probability distribution called the uniform distribution. Here, all the entries are exactly equal and equal to 1 over omega, the uniform distribution. Okay. This is an elementary consideration about combined system. Sometimes you want to consider a system consisting of two subsystems like this. And suppose that microscopic state of subsystem 1 is denoted like J, denoted as J, and it runs from 1 to omega 1. And microscopic state of subsystem 2 is denoted as K, and it runs from 1 to omega 2. And the microscopic state of the whole system is characterized by this pair JK, where J runs from 1 to omega 1, K from 1 to omega 2. So there are omega 1 times omega 2 microscopic states in this system. And then consider a probability distribution in this combined system, which is written like this. And then we have the notion of the marginal distributions corresponding to this. Simply, if you're given this, you just sum over K. This means that you don't look at this subsystem 2, and then you get this quantity, which can be regarded as a probability distribution for system 1. And similarly for here, you just sum over J to get a probability distribution for system 2. Okay? And these are probability distributions and called the marginal distributions coming from this P. And if it happens that this P of JK, original PJK, is the product of this and this for any JK, and so of course this doesn't happen usually. If this happens, then we say that the two systems are independent in the probabilistic sense. We have already seen Janssen's inequality when we discussed the Jarutinski equality in part 1. And let us discuss general case and prove it. So it's an inequality about a convex function. So let phi x be a convex function of x in R. And so if phi is differentiable, this simply means that the twice derivative is non-negative. But here's the more general mathematical definition of a convex function. You don't assume differentiability. And then phi is said to be a convex function if for any x1 and x2 and any lambda between 0 and 1, this inequality is valid. This simply says that this graph of phi is below this line connecting here and here. Okay, so this is the definition. And if you accept this definition, actually you can also prove that the graph really looks like this. So this phi is below this straight line here, and it's above, or it's not less than, not below this straight line in this region. Okay, anyway, that this is more mathematical, so probably this is enough. And the inequality said that for any probability distribution and any state function f, state quantity f, this is valid. And here phi f hat is a state quantity, a random variable that takes value phi fj in state j. Okay, a typical example is, of course, exponential function, which is convex by this property, and in this case, this reduced to this. I think you are already familiar with this. So actually, in this case, in the previous application in the Jarzynski equality, f was a state quantity which takes continuous value. And actually, we're going to discuss a proof which is also valid in continuous random variable case. Okay, so this proof makes use of this useful fact about convex function. What is that? This fact? Well, let phi be a convex function. Then for any x node, there you can take a constant alpha. Actually, this is when phi is differentiable at x node. This is nothing but the derivative at x node. And but this is true even if phi is not differentiable. And in general case, this alpha is called a subderivative. But anyway, you don't have to care. And the main claim is that this inequality is valid for any x. So this simply means that the graph of phi is above this straight line, which is nothing but the tangential line if this is differentiable. Okay, and the proof is very easy. So you have this picture, and so you bring x1 to x2, for example, and then the graph looks like this, and you basically prove this. This is too sloppy, but basically the proof is like this. So, but anyway, we have this inequality. Okay, so let's apply this with this setting. So I will set x to be fj, x naught to be the expectation value of f. And then this inequality becomes like this, yes. And then I multiply everything by pj and add sum over oj. And then this becomes the expectation value. This is already a constant, so this is the same. And this becomes this expectation value, and this does not change. Okay, and these are the same thing, and you get 0. So you get this inequality, which is nothing but Jensen's inequality. Okay, another thing I want to review is, again, I have used this a lot, but canonical distribution, a probability distribution that reproduces macroscopic properties of the equilibrium state of a physical system at temperature beta inverse. That is called canonical distribution. And you consider a physical system with discrete microscopic states J. And for each J, we have a quantity called the energy. Okay? And so this is a microscopic energy of the state J. And canonical distribution P is given by this. And here's the Boltzmann factor, and this is the normalization constant, usually called the partition function. And it's known that the log of z gives the Helmholtz free energy. Okay. And here's a simple observation about system consisting of two subsystems. Consider a physical system consisting of two subsystems 1 and 2, and denote the microscopic states like this. And then the microscopic state of the whole system is characterized by the pair JK. And suppose that the microscopic energy of the state JK is written as a sum of energy of system 1 and energy of system 2. So this means that physically speaking, there is no interaction between system 1 and system 2 because there's no interaction energy. In this very special case, if you compute z of the whole system, and this is sum over all the microscopic state, and this is the Boltzmann factor. But since we have this, this separates into these two sums. So we have, so this is this, this is this. So this z is equal to the product of two partition functions for the system 1 and that for the system 2. And if you look at the canonical, the probability of the canonical distribution, this is the definition, but z splits like this. And also since this E is sum, this Boltzmann factor again splits. And so this can be written as a product of two probability distributions. So in this case, we started from the assumption that there's no interaction between two subsystems. So the two subsystems are independent in the physical sense. If you in the physical sense understood from the form of energy, but this tells you that in the canonical distribution, the two subsystems are independent from the probabilistic sense too. Okay, right. Okay, so these were basically all that I wanted to say about the probability theory. But before going on, let me briefly discuss the physical meaning of probability. Here are typical questions. What does it mean that the probability of an event A is P, for example, 0.3? What does this number mean? For example, you have a button and box here, and somebody says that if you press this button, the box is going to explode with probability 0.3, and you press. And well, if nothing happens, you say that, okay, that's 70%, it's quite likely, but it may explode. Then you say, well, 30% is not a small number. But anyway, it will explode, or it won't explode if you do an experiment. What does this number 0.3 mean? Or you can ask, what does it mean that the expectation value of a physical quantity F is this number? I mean, if you again, make an experiment, then you get a single number fj, okay? If you throw a dice, you never get 3.5, which is the expectation value, okay? So I like to answer, I like to at least provide an answer to these kind of questions. And of course, you don't have to answer these questions to study non-equilibrium statistical mechanics. We can proceed, but we are going to use probability to study physics. So it's better to have at least an answer to these questions. And I also tell you that you usually do not see this kind of discussion in textbooks of probability, because in mathematics, they are interested in probability as a mathematical theory, and they are not interested in this kind of questions. I don't know. I'm not a mathematician, but that's what I think. Okay, so to proceed, we have to make an empirical assumption. And this assumption, which is necessary for relating the probability theory with the physical world, it has a name, and it's called Cournot's principle. Sorry for the bad pronunciation. And there are many different versions, but this is one version. So you pick an event whose probability is very, very, very small. Okay, and after picking this event, you make an experiment, and then it says that then the event A is never true in practice. This is the principle. For example, you pick 8. You have a fair dice, and you pick 8 numbers. Well, to be simple, you picked 8 ones, and you try to get this. You examine if you get these 8 numbers by throwing a fair dice, and of course, the chance of getting this is less than 1 in a million, so you never get it. Okay, that's Cournot's principle. I don't know why this is true. Probably you get it, but anyway, we know that it's reasonable to assume this. But be careful about this order, right? For example, you can just start throwing a fair dice to get 8 numbers. I don't know what, but you get these numbers. These are 8 numbers, and you ask, what is the probability of getting this sequence? And you start computing the probability. Of course, the probability of getting 4 in the first throw is 1/6, and to get the probability of getting this is 1/6, 1/6. And so you find that the probability of getting this particular sequence is very small. It's less than 1 in a million. This is a miracle. You can start arguing that we have seen a miracle because the probability of getting this sequence is very, very, very small. But of course, this doesn't make sense. And the point is that when using this principle, we have to pick an event A before making an experiment. Okay, so that is the point. So this is an empirical assumption. I don't know why we are justified to assume this, but we know that it's reasonable to assume this. Okay, so we need one more thing, which is just, this is a very standard mathematics. You find this in any textbook in probability. That's called Chebyshev's inequality. And it said that for any probability distribution P, any state quantity f and any positive number epsilon, this inequality is valid. What is this? The left-hand side is the probability of this event. This event says that the measurement results of f, the difference between the measurement results of f and the expectation value of f is greater than equal to epsilon. And this probability is bounded from above by the standard deviation divided by epsilon squared. Okay. Here's the proof. It's very simple. It's a trivial inequality. You define a state quantity theta hat by this relation. So if this difference is greater than equal to epsilon, theta is 1 and it's 0 otherwise. And then we claim that this inequality is valid. To see this, it's better to look at this picture here. So this axis represents this thing, fj minus expectation value f, and then this right-hand side will become this parabola. Okay, and the left-hand side is this step function. But we have chosen this coefficient here so that this here you have epsilon 1. So these parabola and these step functions touch here. And of course, it's clear from the picture that this parabola is always above the step function. Okay, so we have this inequality, and you take the expectation value of the both sides, and then the expectation value of the left-hand side is nothing but this probability here. And the right-hand side is this, and of course, this is sigma divided by epsilon squared, QED. Very simple. Okay, now we have this Cournot's principle and Chebyshev's inequality. Then we can answer the question about the expectation value. First of all, suppose that it happened that the standard deviation of f is much smaller than epsilon. And here epsilon denotes the precision for measuring or discussing this physical quantity f. F is a physical quantity, so there should be some precision which is necessary and sufficient for our purpose of discussing physics. Okay, that is this epsilon, and we assume that standard deviation is much less than epsilon. Then then Chebyshev's inequality tells you that this probability is less than this, and this tells you that this is much less than 1. So we see that the probability of this event is very small. And what is this event? Well, this says that the measurement result of f differs from the expectation value more than epsilon. Okay, and then Cournot's principle says that this event is never true in practice. So we can say that in practice the measurement result of f is always equal to f within the precision epsilon. Okay, so that answers this. I think this question. What does it mean that the expectation value of physical quantity f is f? Oh, well, if this condition about standard deviation f is satisfied, then we can say that, well, f is basically what you get when you measure f. Okay, and I wrote here, but probably you are familiar with equilibrium statistical mechanics, and you know that in equilibrium statistical mechanics, this situation is not rare. Actually, this is very common. If you choose proper f, like the density of some physical quantity, then this inequality is almost always valid. It's one of the central reasons that statistical mechanics is useful. Okay, so that can be also true in non-equilibrium statistical mechanics too. So if we happen to have this situation, we are done. Okay, and here's a very short remark about what to do when this is not necessarily small. So if this is not small, what do you do? One way of dealing the situation is that you prepare n exactly identical copies of the same system, and we denote by f hat n the quantity, the state quantity in this nth copy corresponding to this half. And then you consider this average for the whole system. And then it's very easy to find that the average of this state quantity in the huge system is exactly the same as the average of the original f, but the standard deviation of this guy is equal to the standard deviation of f divided by square root n. Then no matter how big this one is, if you can pick large enough n so that this whole things become much smaller than this precision epsilon. And then you can say that the measurement result of this state quantity is always equal to f, expectation value f, within the precision. Okay, so when the standard deviation f is not small, we can answer this question in this way. We didn't deal with this, but actually this has already been answered because probability is a special case of a state quantity. So you can think about this. Okay, so this is the end of this video.